Okay, so in this problem we have a little bit more work to do. We want to take the volume, of a ball, 3-inch radius ball, that has a 1-inch diameter hole drilled through the middle. So first thing we have to figure out is what graph would we have to revolve to generate a ball. Well, what is a ball? A ball is a sphere, right? So a ball is a sphere. And so what do we have to revolve? To get a sphere, we'd have to revolve a semicircle. So we need a semicircle that has a radius of 3. Now, there's lots of semicircles we can do. I've chosen probably what I think is the simplest semicircle, which is a semicircle with radius 3 centered at the origin. Okay. Then we have to understand for our semicircle, what's it going to mean to draw out a hole from the center? Well, that means that if we have our semicircle, we're taking a hole, right? We're basically taking a flat line and cutting it out, and we're actually just going to be looking at this region right here. This region right here. So that's the idea. Let me paste in my graph from Desmos so it looks a little bit nicer. So here's our picture. Right, there's our circle right here, radius 3. That's just the equation right there, y equals square root of 9 minus x squared. And then I have the line y equals 1/2 because it's a diameter 1 circle hole that we're going to drill out. We're going to drill out a 1-inch diameter hole out of our circle. Right, that's what we're planning to do there. So we take our ball and we're going to drill that out. And so I need to know this point right here, 2.95804. Because what I'm going to do is I could do the integral from that point to that point, the whole thing, or I can realize symmetry here, that this graph, of course, is symmetric about the y-axis. So what I'm actually going to do is take this part and then just double it. So I'm going to take this part here and just double it. Okay, so now we're ready to set up and work through our problem here. Okay, so the volume will be 2 pi, and I roll along the x from 0 to 2.958. That's just how far I'm going to round it. 2.958. And it's going to be the top function, which is the circle, square root of 9 minus x squared, minus the inner piece, which is that line y equals 1/2. Okay. And then dx. And so then we just start to compute this now at this point. It's going to be 2 pi times the integral from 0 to 2.958. And then when we square that, that's just going to be 9 minus x squared. That's going to be minus 1/4. So we're going to have 9 minus 1/4 will be 8.75 minus x squared dx. And then we do our integral. So 2 pi on the outside. And that's going to be 8.75x minus x cubed over 3. Evaluated again between our two endpoints, 0 and 2.958. Now, when I do that computation, I'm going to have 34.51 pi, working out this part, and then simplifying with the pi, I get a volume of 108.42. And this was a 3-inch ball, so that would be cubic inches. Okay. This was originally a 3-inch ball, going back to the top of the problem, so that would be in units of cubic inches. Units of cubic inches. Now, a few things just to kind of verify that this makes sense, this answer. If we were to do the volume of a ball, a 3-inch ball, the volume of a sphere is 4/3 pi r cubed. So that would give us a volume of 113.097 total cubic inches. Now, if we're taking a cylinder out, cylinder of radius 1, cylinder of radius 1/2, the volume of a cylinder is pi r squared h. Now, a full cylinder that went from the top to the bottom that we took out would have a height of 6. So that would be pi times 0.5 squared, a 1/2 inch squared, times the height of 6. And that would be 4.7. Now, if you took that away and you did your original volume, 113 minus 4.7, that gives you a volume of 108.38. But what you have to understand, have to realize, is some of that cylinder is actually not cutting, right? That 1/2 inch cylinder would actually be containing air. Some of that volume of that 1/2 inch cylinder that I'm taking out is containing air, because only the very tip of that is actually cut out. So, and the same thing on the bottom. And so that's the difference here. That extra little 4/100ths of a cubic inch that was getting cut out has disappeared, because that was actually would have been the air, because only the first part of that, if you zoomed in real far, right, the first part of this thing, right, would have the whole 1/2 inch. You'd be having this air part that's considered in the volume of the cylinder that actually isn't getting cut out. That's why our answer, of course, is accounted for that. And that's why it's slightly more, our object has slightly more volume than if you just thought of it in terms of a sphere minus the cylinder that you took out. And that's why we had to look to that particular point there to be able to work that out. Okay, so hopefully this kind of gives you a little example of some of the cool things you can do with calculus here with these volumes of solids of revolutions.